Okay, this is the problem statement for the in-class settling problem, as well as a schematic showing the water elutriator. A few things to note here. We have an upward flow of methanol instead of the traditional water, so that will influence the system, because we have a different viscosity and a different density for methanol than we do water, so we'll need to make sure we account for that. We're given that there's 17 weight percent of each particle types, and that there's two particle types, quartz and gold, and the quartz has a diameter of 500 microns, which is quite large. Gold has a diameter of 5 microns, which is quite small. The elutriator length in the vertical is 550 centimeters, and we're asked a series of questions that there's an upward flow of methanol 1.5 times 10 to the minus 3 centimeters per second, and we're asked at what time in minutes is 50 weight percent of the gold left in the elutriator. We're also asked what is the minimum methanol flow velocity that would cause 100% of all solids to report to the underflow in the system. And so I'm going to go through this on a step-by-step basis that will give you kind of the process by which to attack these settling problems. There is a definite format and flow that we want to follow, and I'll go through that step by step, and eventually then when we have the knowledge of the settling velocities, we can answer these two questions that are posed to us. So let's start by just kind of laying out the parameters of the system, at least from a particle perspective. We've got two particles, SiO2. We're given that it's a diameter of 500 microns. We're gonna convert that to centimeters and be working in CGS units. So the diameter is 500 times 10 to the minus 4 centimeters. In terms of the radius, then it's half that value, 250 times 10 to the minus 4 centimeters. And of course the density of SiO2 equals 2.65 grams per cubic centimeters. So we're going to be working in CGS units. So that's one of the particle types. The other particle type in this system is gold. We'll do a similar breakdown in terms of CGS units for gold. Here the diameter is 5 times 10 to the minus 4 centimeters. Radius, half that value. There is a very large difference in density between the two particles, and we'll see that both the diameter difference and the density difference will dramatically influence the settling velocity of these two particles. But the gold particle is smaller, but has a higher density. The diameter of quartz is much larger, but with a lower density. So let's start then with quartz, and we could start with either one of these particles, but we'll start with quartz. We could start with gold, but we'll just start with quartz. Always we're going to assume Stokesian settling conditions first. We'll check Reynolds. We'll calculate a Stokesian settling velocity. We'll check Reynolds number. If it's less than 1, then that means our settling velocity assumption is correct. If it's greater than 1, we're going to have to use the Hahn approach. But let's go ahead and assume Stokesian settling for quartz. And we'll use the Stokes settling equation. So I've written out the Stokes settling equation, putting in the radius of quartz, the density difference between quartz and methanol, the gravitational constant, as well as dividing by 9 and the viscosity of methanol. If I perform that calculation, I get a settling velocity of 34.2 centimeter per second. Now I need to check Reynolds number. Multiplying the diameter of the quartz particle by the calculated settling velocity times the density of methanol divided by the viscosity of methanol. And I get a Reynolds number of 182.6. Of course, that's a dimensionless number, and it's much, much greater than 1, which means then we need to use the Hahn approach. In other words, Stokesian settling is not valid for quartz. So we're going to move on and use the Hahn approach now that we've calculated a Reynolds number greater than 1. And so we put in the system constants, the viscosity and density of methanol, as well as our particle diameter, all times 10 to the A power, which gives us a value of 0.19 times 10 to the A power. Now, of course, we have to calculate that exponential constant A. So A has a rather long value, and included in that is the Galileo number, which we'll calculate separately here. And we calculate that the Galileo number in this case is equal to 3,287.1. It's also a dimensionless number. We can go on to calculate an A then in the equation above, 1.7244. And we put that back up in our settling velocity equation. We can calculate a terminal settling velocity of 10.07 centimeter per second. So now we have terminal settling velocities for both particle types. All right, I take that back. That was, I was talking about gold there. clearly we were calculating the terminal settling velocity for SiO2 here using the Hahn approach. Now we need to move on to calculating the terminal settling velocity for gold. We're going to do much the same. We're going to assume Stokesian settling for gold using Stokes's equation, putting in the parameters for gold. And we calculate then a Stokesian settling velocity for gold equal to 0.034 centimeters per second. We need to calculate Reynolds number based upon this settling velocity. If we do that, we find that the Reynolds number is equal to 1.8 times 10 to the minus 3, which is much less than 1. So therefore, we can say that Stokesian conditions are valid. And we can use 0.034 centimeter per second as our terminal settling velocity for gold. So now we've established the relevant settling velocities for both particles. For quartz, we had to use the Hahn approach. Here with gold, we can get away with using Stokesian settling simply because that Reynolds number is less than 1. So next up, we need to check free versus hindered settling to determine if we need to calculate a correction factor or not. And so we're going to calculate a volume fraction solids. And it's simply a fraction. The top part of the fraction is the numerator there is a reflection of the weight fraction of each particle type divided by the density for that particle type. And since both particle types are at 17 weight percent, the weight fraction is 0.17, and we divide by the respective densities. And those numbers translate down at the bottom as well. Same fractions. But we need to account for the fraction of methanol. Now you may wonder where the 0.66 comes from. It's that we're doing this on a 100% basis, and so if there is on the weight fraction, it would be on the fraction of 1 then. So the solid quartz, solid gold, and here the 0.66 is the difference, 1 minus those values, or 0.66 divided by the density of methanol, which is 0.79. And if we do that calculation, then we get a gamma value for the solid fraction is equal to 0.08. And we've determined previously that if the volume fraction solids are greater than 1% or 0.01 volume fraction, hindered settlings occurring. So we're going to have to calculate a correction factor. If the value was less than 0.01, we could use those free settling conditions, but in this case, we're going to have to calculate a hindered settling correction factor. So let's go ahead and do that. We abbreviate the correction factor C sub F. And there's two regimes that we define for the correction factor, and we're in the lower end of the volume fraction, so we'll use this equation. Should be 1 minus 2.5 minus, getting a little scrunched on the edge. The correction factor is equal to 1 minus 0.08 to the 2/3 power times the quantity 1 minus 0.08 times the quantity 1 minus 2.5, and my 2.5 should be, so it's 1 minus 2.5 times 0.08. Since I'm scrunched over there, I'll rewrite that little part here. It should be 1 minus 2.5 times 0.08. Okay. So I'll go ahead and do that calculation, and I'll calculate a correction factor of 0.6, which in essence means that because of the high solid content in this system, there will be particle-particle interactions, which slows the settling velocity of the particles down by a factor of 0.6, or you could think of it as 60%. Let's go ahead and apply that correction value for our systems, starting with SiO2. So I'm taking that settling velocity we calculated earlier using the Hahn approach, 10.07 times our correction factor, to get a corrected settling velocity for quartz of 6.04 centimeter per second. I want to do the same thing with gold. So I multiply that terminal settling velocity that we found with Stokes' equation times the correction factor to get the terminal settling velocity for gold. So those will be the two settling velocities that I'll utilize. Now we can start to think about answering the two questions we were given initially. The time in minutes when 50% of the gold is left. And you want to think of this in terms of the distance of that elutriator. It was 550 centimeters. 50% of the gold then would travel half that value, or $225 centimeters. 275 centimeters is half that distance to 275 centimeters. Our upward flow of methanol, or velocity of methanol, that was given at 1.5 times 10 to the minus 3 centimeters per second. 1.5 times 10 to the minus 3 centimeters. But we've calculated a downward velocity of gold. Is that corrected value? It's 0.02. So these are conflicting. The methanol's flowing up, the gold is flowing down. So we have to get a net velocity of our particles. The net velocity of gold is the difference between these two. Or 0.02 minus 1.5 times 10 to the minus 3, since it's counteracting, giving us a downward velocity of 0.0185 centimeter per second. Downward net velocity. Now, so that's the net velocity of gold. It has to traverse 275 centimeters for half of it to leave the system. So I look at my units and I recognize that I've got centimeters in two places. So I'm going to take 275 centimeters, my distance. I'm going to invert this velocity. Of course, the centimeters term cancel, and it leaves me with 14,865 seconds for 50% of the gold to leave the system. I can convert seconds to minutes as requested. I'm going to take that 14,865 seconds, multiply 60 seconds per minute, which gives me a value of 248 minutes for 50% of the gold to leave the system. And I'm asked the minimum methanol flow to cause 100% of the particles in the overflow. So to cause all of the particles to go out that overflow. So just making some notes here. For that to happen, we would need a flow in excess of 6.04 centimeter per second, simply because the downward flow of SiO2 is the greatest of the two particle types. And so we need to increase the methanol flow greater than 6.04 centimeter per second. That would cause all of the particles, both SiO2 and gold, to flow out. Of course, the gold would flow out first because it has a much lower settling velocity, and then all of the quartz would flow out. So we've been able then to answer both of these questions that were posed to us. And that's going to be the process you want to follow again and again. You want to assume Stokesian settling velocity. If Stokesian settling velocity isn't true, you'll calculate the settling velocity using the Hahn approach. You'll check to see if you have free or hindered settling. If hindered settling is occurring, you're going to have to apply a correction factor to the settling velocity that was calculated earlier.